When old satellites fall into Earth's atmosphere and burn up, they leave behind tiny aluminum oxide particles that erode the Earth's protective ozone layer. A new study reveals that these oxides have increased eightfold between 2016 and 2022, and they will continue to accumulate as the number of satellites in low Earth orbit rapidly grows. The 1987 Montreal Protocol successfully regulated ozone-depleting CFCs to protect and restore the ozone layer, with the ozone hole over Antarctica expected to recover within 50 years. However, the unexpected rise in aluminum oxides could halt the progress of the ozone layer's recovery in the coming years. Out of the 8,100 objects in low Earth orbit, 6,000 are Starlink satellites launched in recent years. The demand for global internet coverage has led to a rapid increase in the deployment of small communication satellite constellations. SpaceX leads this initiative, with permission to launch 12,000 more Starlink satellites and plans for up to 40,000. The study's authors note that Amazon and other companies worldwide are also planning constellations ranging from 3,000 to 13,000 satellites. The lifespan of internet satellites in low Earth orbit is about 5 years. Companies must then launch replacement satellites to maintain internet service, perpetuating a cycle of planned obsolescence and unplanned pollution. Aluminum oxides trigger chemical reactions that deplete stratospheric ozone, which protects the Earth from harmful UV radiation. These oxides don't chemically react with ozone molecules directly. Instead, they trigger destructive reactions between ozone and chlorine, depleting the ozone layer. Since aluminum oxides are not consumed by these chemical reactions, they can continue to destroy ozone molecules for decades as they drift through the stratosphere. Despite this, little attention has been given to pollutants created when satellites burn up in the upper atmosphere. Previous studies on satellite pollution mostly focused on the consequences of rocket fuel release during space launches. The authors from the University of Southern California's Viterbi School of Engineering state that the new study provides the first realistic estimate of the scale of this long-lived pollution in the upper atmosphere. Joseph Wong, a researcher in astronautics at USC and a corresponding author of the new study, said, "People have only recently started thinking that this might be a problem. We were among the first teams to look into what these facts could mean, since gathering data from a burning spacecraft is virtually impossible. Previous studies used analyzers of micrometeoroids to estimate potential pollution. However, micrometeoroids contain very little aluminum, unlike most satellites, which are 15% to 40% aluminum by mass, making those estimates less applicable to new swarm satellites. To get a more accurate picture of pollution from satellite re-entry, researchers modeled the chemical composition and bonding within satellite materials as they interact at molecular and atomic levels. These results gave the researchers an understanding of how the material changes with different energy inputs. Researchers found that in 2022, aluminum levels in the atmosphere increased by 29.5% over natural levels due to satellite re-entries. Modeling showed that a typical 250 kilogram, 550 pound satellite, with 30% of its mass being aluminum, would produce about 30 kilograms, 66 pounds of aluminum oxide nanoparticles, 1 to 100 nanometers in size during re-entry. Most of these particles are created in the mesosphere, 50 to 85 kilometers, 30 to 50 miles above Earth's surface. The team then calculated that depending on particle size, aluminum oxides could take up to 30 years to descend to the stratospheric heights where 90% of the Earth's ozone resides. Researchers estimate that once the currently planned satellite constellations are complete, 912 metric tons, 1005 US tons of aluminum will fall to Earth annually. This will release approximately 360 metric tons, 397 US tons of aluminum oxide into the atmosphere each year, a 646% increase over natural levels.